In exercise 7H, we're going to see a change in focus. So far, we've really looked at the process of differentiation, the mathematical understanding of what the derivative is giving us in terms of the graph and tangents and normals, etc. What we're actually going to move on to is one of the first applications of the derivative. So just a little bit of, I guess, not so much review, but just I want to establish a few things before we move into that. When I write dy dx, you know that is possible if I have a function a function called y, and it is something to do with x, like x squared plus 2, x squared plus 2, something like that. Dy dx would not be possible if y was t squared plus 2. Because dy dx is telling us definitely that we're differentiating y with respect to the x variable. When there's no x variable, as in this case, we cannot find dy dx. Of course, we could find dy dt. So I just want to draw that to your attention, because we're going to find we have some situations where we do want dy dx, or we might want dy dt. However, our function will need some alteration so that we can actually carry out the derivative that we need to. Now, when I say that we need to, it's because we have an understanding of what this derivative is getting for us. The derivative is getting for us, we know mathematically it's getting for us an expression for the gradient, but there is a real understanding, a real life understanding to that, which has got nothing to do with gradient and tangents. It could, for example, as I've got here, because the derivative gives us the gradient, and the gradient measures rate of change, and the rate of change is measuring how one quantity is, as it says, changing relevant to another, then we could talk about speed as a rate. So we've got that. If, for example, I had an expression about distance, for example, the distance travelled is the time squared plus 5 times the time. So I've got an expression for d in terms of t. It stands to reason I could mathematically find dd, differentiate this expression d with respect to t, yes. The other thing about this is that it represents in real life the change in the distance with respect to time. That actually is a quantity that we refer to as speed. So the derivative is giving us another quantity that we understand. Another example is if we had volume, an expression for volume, and we called it V, and if this the volume, say, of water in a tank, the volume of water in a tank, we're trying to fill a tank, or the water in the pool, we're filling the pool. If we have the volume expressed in terms of the time, then we could mathematically calculate dV dt, and what that would be giving us would be the rate of change of the volume, the rate at which the water was going into the pool. the rate at which the pool was filling. Now, there might be other situations where we're interested in the volume changing with time. If we're looking into comparing different cars and we want to know the rate at which the volume of petrol is being used with respect to time from one car to another car, then that's an interesting feature, or from one engine to another engine, that the engineers would be looking at, and maybe they're trying to improve the rate or decrease the rate at which the volume of petrol is being consumed with respect to time. There are many applications for the derivative, and it's important for you to realise that the derivative mathematically gives us the gradient, but in real life terms, it gives us a rate of change. If we think about the volume, however, is rarely measured in terms of time. It's rarely measured in terms of time. But it may be really critical to our investigation that we're measuring the volume with respect to time. Volume, you probably know, if it was the volume of a sphere, it's in terms of its radius. If it was the volume of a cylinder, again, it is in terms of its radius and height. If it was the volume of a cube, it's in terms of its side length cubed. So we have various formulas that we are going to call on, and we need to set these formulas up such that they will allow us to differentiate with respect to a particular variable. Of course, there's no problem if your volume is like this. Volume is in terms of there is only this one variable, and you wanted to know the rate of change of the volume with respect to the radius of the sphere. That's perfect. Or if you wanted to know the rate of change of the volume with respect to the length of the side of the cube, this one here presents a problem, because do we want to look at the rate of change of the volume with respect to the radius, or do we want to look at the rate of change of the volume with respect to the height of the cylinder? Here we have a real problem. But like I said, we're often, and the engineers and the scientists are often far more interested in finding the rate of change of, say, the volume, not with respect to any of these variables, but rather with respect to time. And so we have to have a look at some situations where that's the case and see what changes are necessary. Now, to do that, we just introduce some actual fraction work, where the fractions are made up of derivatives. So, if we have a look at dv dt, we probably never thought of it like this before, but what we could actually say, because mathematically dv dt is a fraction, it could be equal to dv dr, and if our volume was in terms of r, like with the sphere, then that would be possible. And we would need to multiply by dr dt, because what would that be allowing? This is mathematical fractions and we're multiplying. You can cancel out these terms, and of course dv dt would equal dv dt. This we can see we can do. We can differentiate volume with respect to the radius of the sphere. And this dr dt piece of information, the rate at which the radius is changing with respect to time, is either something we can also calculate, but more commonly is given. So one of these rates will be given. One we will be able to find by using a formula. We'll be able to differentiate a formula with respect to time. And like I said, the other will be given. Now, we won't be always talking about volumes and radiuses and times. So in general, what we say is that, more generally, we go back to our dy/dx, and we say that dy/dx can actually always be broken up into dy/du. Introduce here, this u being whatever is convenient for us to introduce. And you would also know, because you'll want mathematically to be able to cancel these two out, that it'll be du and obviously dx. So a particular variation on that might be that if we want dy/dx, we might talk about dy/dt, as long as we multiply it by dt/dx. Now, these are going to be some expressions that we're actually going to be able to find and substitute. The other added complication is, if we look at this, for example, dy/dx is dy/dt times dt/dx here, then we've got three separate components. In any one equation, you may be finding this one, dy/dx, which means that you'll have to be able to find or be given dy/dt, likewise dt/dx. Or on the other hand, you might be given dy/dx, you might be given dy/dt, and you would be able to find dt/dx. So it's almost like we think of this as three different separate aspects to the equation, and of course you could be calculating any one of those, provided you have the other two. Sometimes students get a little bit lost in what notation to actually use here, maybe what abbreviation to use, and I think that obviously a good read through might help you out in the question. So if the question is talking about the rate at which the volume is changing, then you'll want dv, and if it says with respect to the radius, then you want dr. Another good indicator are the units that are used. For example, if you were told to produce something in terms of square meters per minute, that you're going to give your answer in square meters per minute. It's clearly a rate. We could find it by finding a derivative. We may have to break our derivative up. However, in order to notate it correctly, meters squared would be a measure of area. Meters squared. So it would make sense to call it dA. Per minute means we want to differentiate with respect to time. Minutes is a measure of time. Meters cubed per minute. Now, meters cubed would measure volume. We want dV dt. Just straight out centimetres per hour could be differentiate distance, because centimetres could be a measure of distance with respect to time. It could just be the length of something. I'm measuring the length of the desk with respect to time. Or it could be dr dt, because you measure the radius. There's an infinite number of things actually that can go there. You might have been thinking width. You might have been thinking height of a cone, etc. Mils per minute, then I think you would see that we're differentiating volume. I'm going to stop the video there.